Good evening, boys and girls. Welcome to another lesson on Technical Sciences Grade 12. We are continuing with organic chemistry and we are dealing with the section on physical properties. Now, remember what I said to you, a very important section counts a lot of marks altogether. So, you need to be very much well acquainted with this section of the work, and hence we are dealing with different types of questions that they can actually ask you, and that is going to definitely cement our knowledge, and we will definitely do better in this section of the work on paper 2 at the end of the year. So let us look at the structure of the lesson for today. We are just going to get a quick review on physical properties as per the examination guidelines. And this is really just to highlight perhaps some of the learners that are joining us for the first time today. And then in the features of the topic, we will be looking at physical properties, and we will learn more of it through answering quite a number of questions that are structured. And then I will still give you more tips on how to prepare for this section for your end of the year examination. I really hope that you did well in your preparatory examination, because I am aware that all of you are done by now, and you will do better in your final examinations. Right, under physical properties as per the examination guidelines, remember we are dealing with 3 physical properties, which is the boiling point, the melting point, as well as the vapor pressure. And then under these physical properties, we must be able to discuss their relationships with regards to all these homologous series that are noted here. For example, we must be informed about the boiling points, the melting points, and the vapor pressure of all organic molecules that belong to this homologous series. Then we must be able to compare physical properties of different homologous series. That is obviously comparing the boiling point, the melting point, and the vapor pressure of organic molecules from different homologous series. And then, given an example of any molecule from this homologous series, I must be able to explain the relationship between any of these, either the boiling point, the melting point, and the vapor pressure, with regards to the strength of intermolecular forces. Basically, how does the strength of intermolecular forces affect any of those 3 physical properties? And how does the type of functional group, which actually determines the type of intermolecular forces, how does it affect any of these 3 physical properties? The chain length, which is the surface area, as well as branching of the chain, how does it affect the boiling point, the melting point, as well as the vapor pressure? Then, furthermore, I told you, you must know how to define all those 3 physical properties, which is the boiling point, the melting point, as well as the vapor pressure. All those definitions are important, and you've seen them in previous examination papers, and we will ask you to define all those definitions. Furthermore, remember, these definitions, you must know them off by head, and you must understand them. And when you write them down as well, you need to write them exactly as I have given to you there, because that is how we are going to mark them. And remember, the pattern that we are following now in terms of asking you these questions is that we actually give you 2 or 0. In other words, everything has to be correct for you to get a mark for that particular definition. For example, your boiling point, your melting point, or your vapor pressure. If any of the keywords here are omitted, then the definition is incorrect, and therefore will give you a 0. So we are really moving away from part marking, which is basically marking the first part of the definition and the second part of the definition. We are really moving away from that. So know your definitions off by head and understand them, and ensure that as you give them, all the keywords are there for you to be able to get all the marks. Then we discussed physical properties, just to refresh your memory so that we are able to answer the questions that will follow. Remember, we must know the relationship between the vapor pressure of a molecule as well as the boiling point. And we note that if an organic molecule has a high boiling point, then its vapor pressure is going to be low. And we know the opposite is true. If the boiling point is low, then the vapor pressure of that molecule is going to be high. So remember that. Again, remember, if the boiling point is high, then I know the melting point is definitely high as well, but the vapor pressure is low. Again, we note that if the boiling point is low, then the melting point will also be low, but the vapor pressure is going to be high. So remember that. So every time the boiling point is high, we know that the melting point must also be high. Every time the boiling point is low, we know that the melting point is also going to be low. Then we look at physical properties and intermolecular forces and how they actually relate. And we know all those physical properties, which are your boiling point, your melting point, as well as the vapor pressure. We know they depend on how strong the intermolecular forces are. Now, in this bullet, we know that if the intermolecular forces are strong, then the boiling point will be high, and then the melting point is also going to be high, but the vapor pressure is going to be low. What else do we note here? If the intermolecular forces are strong, then you require more energy to overcome those intermolecular forces because they are strong, or basically more energy to break those intermolecular forces. So you can use either of the terms, breaking the intermolecular forces or overcoming the intermolecular forces. Now, we are using the term intermolecular forces. We are not using the term bonds. So you cannot say to me, the energy needed to break bonds. We are not breaking the bonds. We are breaking the intermolecular forces altogether. Right. Now, what else do we note? We note that the opposite is also true. If the intermolecular forces are weak, then the boiling point will be lower, and then the melting point will be lower, but the vapor pressure is going to be higher altogether. And what does that tell me again? It tells me that if the intermolecular forces are weaker, then less energy is needed to break or to overcome the intermolecular forces. Then we talked about different types of intermolecular forces. We talked about hydrogen bonds, we talked about London forces, and we talked about dipole-dipole forces. And we recall that the London forces are more important in organic molecules that are alkanes, alkenes, and alkynes. And they are the weakest of all intermolecular forces. And then we noted the hydrogen bonds. For our syllabus, we will get them in alcohols and carboxylic acids. And we know they are the strongest of all intermolecular forces. Furthermore, we recall that even though alcohols have hydrogen bonds and carboxylic acids have hydrogen bonds, the hydrogen bonds in carboxylic acids are much stronger than the hydrogen bonds in alcohols. And we know those in carboxylic acids, they are definitely stronger than in alcohols because carboxylic acids have two sides for hydrogen bonding, but alcohols only have one side for hydrogen bonding. And that is why we say the hydrogen bonds in carboxylic acids are stronger than the hydrogen bonds in the alcohols. Right. Now, let us move to a question. And I thought we must be able to do more of these questions that are on experimental type of questions, because we have dealt with other questions where we were not dealing with questions of a practical nature, where we were not identifying variables and so on. So since yesterday we dealt with at least one question that is experimental, and today I want to do the same so that I am able to concretize this topic, and so that you are also able to answer any form of question that you get. Now, we are given a scenario here. They tell us 3 hydrocarbons, A, B, and C, with molecular formula C5H12 are used to investigate the effect of branching on the boiling point of hydrocarbons. The results obtained are shown in the table below. Now, here I've read it once, and there isn't much that one also picks up, and hence you go back to the question, read it slowly, and highlight what is important. Now, my dear learners, we are being told that three hydrocarbons, which are named A, B, and C, they all have a molecular formula C5H12. In other words, all these hydrocarbons A, B, and C, they have 5 carbons and 12 hydrogens in their molecule, in their structure. And they are used to investigate the effect of branching. So this tells us that we are branching a molecule. And we know that if a molecule is being branched, it means the carbon chain, which is the parent chain, it is being reduced, because other carbons are now going to form a substituent. They are now going to be part of a branch. In other words, when I look at these hydrocarbons that they are talking about, then it means branching is being effected on these hydrocarbons. So I'll be having molecules that are branching in one experiment, and in the other experiment, the molecule is being branched even more. And what they are doing is they are actually trying to find out the effect of branching. What does branching do to what? To the boiling point of these hydrocarbons. In other words, they are trying to find out what happens to the boiling point when a molecule is being branched. Most definitely, it tells me they are trying to check What happens to the boiling point when you branch? Meaning, does the boiling point increase when you branch a molecule, or does the boiling point decrease when you branch a molecule? So that is what they are trying to find out. The results obtained are shown in the table below. Now, let us revert back to our theory. We note that the more you branch a molecule, the more you are reducing the size of the parent chain. Because now, when you branch, it means one carbon is removed from the parent chain and it will form a branch. In other words, the chain length actually decreases. So when you branch a molecule, the chain length decreases. In other words, the surface area decreases. Now, from our theory, we note if the surface area gets smaller, or a molecule that has a smaller surface area, or a molecule that has a smaller, or rather a shorter chain length, we know that the intermolecular forces are going to be weaker. Now, when the intermolecular forces are weak, we expect that the boiling point will be low. But if a molecule doesn't have a lot of branches, it is less branched, or the molecule is a straight chain, meaning it doesn't have branches, it means its surface area is going to be larger. It means the chain length is going to be longer. And when the chain length is longer, I know that the intermolecular forces that are acting on that molecule are going to be stronger. And if the intermolecular forces are stronger, it means the boiling point is going to be high. Now, let us look at the results obtained when a molecule is being branched. Now, there I've been given my hydrocarbons, which is A, B, and C. And then on the other side, I've been given the boiling point. Again, we can see that the boiling point is measured in degrees Celsius. Now, what does this mean? Let us look at the pattern here, or what we call the trend, because we can ask you to explain the trend in the boiling point, let's say from A to C. And if I ask you to give me the trend in the boiling point from A to C, remember, I am simply saying to you, give me the pattern in terms of boiling point from A to C. What is happening to the boiling point from A to C? That is what I'm asking you. And I can see that from A to C, the boiling point is decreasing. Why are we saying it is decreasing? Because in A, it is 36 degrees Celsius. In B, it is 28 degrees Celsius. In C, it is 10 degrees Celsius. So the trend here in boiling point, or the pattern in boiling point, is that it is decreasing from A to C. My dear learners, I am also expecting you to answer it exactly as given, because we asked for the trend in the boiling point from A to C. So you can't answer in terms of C to A altogether, right? So the boiling point is decreasing. Again, these molecules, they told us that this molecule is a C5H12. B, it is also a C5H12. Molecule C, it is also a C5H12. Now, these three hydrocarbons, I can see that they have the same molecular formula because they're all C5H12. That is what they told us there. And these molecules, they have different boiling points. In other words, these C5H12s molecules, which are these hydrocarbons, they cannot have the same structure, or rather they cannot have the same structural formula. Why? Because if they're all C5H12 and they all had the same structural formula, then they should have the same boiling point. But because they have the same molecular formula, but the boiling points are different, tells me that the structural formula are also different. Now, this tells me that hydrocarbon A, B, and C are organic molecules with the same molecular formula, but they have different structural formula or structural formulae. Why? Because the molecular formula are the same there, but the boiling points are different, so the structural formula are different. In other words, when I look at A, B, and C, I am talking about isomers, or what we call structural isomers. Now, let us draw three structural isomers of C5H12. The first thing that we see is that these molecules are all hydrocarbons. So, let us draw one of the isomers. It's carbon. It must be 5 of them. 1, 2, 3, 4, 5. Then let us check. And this is definitely an alkane because you can see it from the general formula. But let's see if it's definitely an alkane. Remember, around each carbon atom, I need to have 4 bonds. Right. So I'll put my hydrogen. I can see everything there. It's 4 bonds. All that I really have to do is just to put my hydrogens. There we go. So I have 5 carbons. If you check the hydrogens, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So correct. That is the first isomer. Let us look at another isomer. Remember, to get another isomer here, my dear learners, because this is a hydrocarbon, there is no way that you can change the functional groups, so you can't make functional isomers. There is no way that you can say, I have shifted the hydrogen or whatsoever, or the bond. So you can't make them positional isomers. So the only thing that you can do is to make them chain isomers. In other words, this is a straight hydrocarbon chain. So make it rather a branched hydrocarbon chain. And to branch it, it means you need to remove one carbon in the parent chain. So now the parent chain must have at least 4 carbons. So I'll go 1, 2, 3, 4. Then I took 1, 2, 3, 4. So this carbon, I'm going to make it a branch. So I will go there and I'm going to put it there. Why can't I put it on the first carbon? If I put it there, this actually won't be the first carbon. So the longest chain would then be 1, 2, 3, 4, 5. So it wouldn't be a branched chain. Then I took the 5th carbon and I put it there. So I'm just left with hydrogens, making sure around each carbon I have 4 bonds. So this would be 1, the 2nd bond, the 3rd bond, the 4th bond. 2nd, 3rd, 4th bond. There's 2 bonds already, the 3rd one, the 4th one. There's 1 bond, the 2nd one, the 3rd one, the fourth one. There are 2, 1, 2, 3 bonds, so the fourth one. Then hydrogens, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is definitely an isomer. Then let us draw another isomer, and then we'll try to identify which one is A, which one is B, and which one is C. So there I'm going to have 1, 2, 3. And why am I having 3? Remember, when you make chain isomers, you have to shorten the parent chain. So from the first one, right, I shortened it from 5. Okay, it was 5 carbons long. The second one, I shortened the parent chain to 4. So the third isomer, I will shorten further, so it will be 3. So it means this carbon atom is now going to form a branch. So, okay, this one is already this one. So now I take the one which was the fourth one, the one that was supposed to be there, and I'm going to put it there. So now you can see the parent chain is 3 carbons long. Whatever direction you go, 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. So it doesn't matter how you go. Then around each carbon, I must have 4 bonds. So it has 1. So this will be the second, the third, the fourth bond. I already have the first, the second, the third, the fourth bond. Here I have the first bond, the second bond, the third bond, the fourth bond. Here I have the first bond, so I'll have the second bond, the third bond, and the fourth bond. Then I put my hydrogens, so 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So all these molecules are C5H12 altogether. So they are definitely isomers because the molecular formula is the same, but the structure is not the same. Now this one is the molecule with the largest surface area. Why? Because it has 5 carbons in the parent chain. 1, 2, 3, 4, 5. So the parent chain has 1, 2, 3, 4, 5 carbons altogether. So it has the largest surface area. Now, if it has the largest surface area, it means it will have the strongest intermolecular forces. So if it has the strongest intermolecular forces, then it must have the highest boiling point. Then I go to my table. Which one has the highest boiling point? I can see that it is A. In other words, this is hydrocarbon A. Then I go further and I check this one, the second one. The longest chain without breaking of carbons, which is the parent chain, is 1, 2, 3, 4 carbons long altogether. So it means this one is somewhere in between this one and that one. Because when I look at this one, it has in the parent chain 1, 2, 3 carbons altogether. So this one must be the one with a boiling point that is between this one and this one. So this one is B, because its surface area is less than the surface area of A. The surface area of B is less than the surface area of A, but the surface area of B is larger than the surface area of C. So automatically that tells me it must be hydrocarbon C. Why? Because this is the one with the shortest chain length. This is the one with the smallest surface area altogether. So it must be the one with the weakest intermolecular forces. So it must be the one with the lowest boiling point. So if this one has the lowest boiling point, then we'll identify this one as C, and then we will identify this one as B. Right. Then we are asked in 16.1 to write down the term used to describe these compounds with the same molecular formula, but with different structural formula. And we say they are structural isomers. We know all of these are structural isomers because they have the same molecular formula, but different structural formula. So these are called structural isomers. If you don't want to call them structural isomers, you simply call them isomers. That is acceptable because all isomers are structural isomers. Now, in particular for the questions that we were looking, rather for these isomers that we were looking at, then we know that these are your chain isomers. And why do we say these are chain isomers? Because they are organic molecules with the same molecular formula, but with different types of chains. Why are we saying these chains are of different types? Because this one is a straight chain. A doesn't have a branch. B is less branched because it only has one branch. C is more branched because it has that branch, because we didn't count that in the parent chain. This one is also a branch. So this one has two branches, so it is more branched altogether. And that is why we say the chains are different types. I have a straight chain in A, I have a less branched chain in B, and I have a more branched chain in C. Then 16.2, we are required to write down for this investigation the following: the dependent variable, the independent variable, as well as the controlled variable. And I want us to start with the independent variable. Remember, I said to you, and this is not the scientific definition, but to make it easy for you, an independent variable is the variable that the investigator is changing. So we have to check which variable are we intentionally changing as the investigators. And what we are actually changing here is the chain length altogether. We are changing the chain length because if I go from A to B, the chain length is decreasing. If I go from B to C, the chain length is decreasing. So to put this simpler for you, the variable that we are changing is what we call the chain length, because the size of the parent chain is decreasing. And you know I prefer to start with the independent variable, the chain length, or what we call the surface area. Now, if you want to really stick to what has been given, which is also what I would advise, the variable that we are changing here is actually the branching of the hydrocarbon altogether. What we are changing here is the branching of the hydrocarbon. Right, and this is more accurate, but we'll still accept even if you say branching will give you the benefit of the doubt. But for clarity, this is definitely the branching of the hydrocarbon because we branch it. So as we branch it, that is intentionally what the investigator is doing. So that is the independent variable, the variable that we are intentionally changing as the investigators. And now, what happens when we change the chain length? Then the boiling point is going to change. So, do you agree with me that the boiling point depends on the length of the chain? And that is why we say it is the dependent variable, because this boiling point here will depend on the chain length. So when you change the chain length and you decrease it, for example, the boiling point decreases. When you change the chain length further and decrease it, or when you branch and continue to branch, the boiling point decreases. In other words, the boiling point decreases because of the chain length. So the boiling point depends on the chain length. Then we are asked to also write down the controlled variable. Now, another term that we use for the controlled variable is that we call it a fixed variable. Now, what are we talking about when you talk about a fixed variable? It means the variable that the investigator is not changing, so that these results can actually be reliable and valid. So, and even more correctly, so that they are valid, right? So that they are correct. Now, we are saying a variable in science, when you perform an experiment, you can't change two variables at the same time. You must actually have one independent variable altogether. So other variables have to be controlled. So if I were to change two variables at the same time, then I wouldn't know why the boiling point was changing. So you can't have two independent variables, you must have one. So other variables must be controlled. And what are we controlling here? If I am using isomers, the molecular formula is the same. So if you go and calculate the relative molecular mass, you will see that it doesn't change. So the answer there must be relative molecular mass altogether. Sometimes, okay, let me just put it like this. The answer there must simply be relative molecular mass, because the relative molecular mass is going to be the same. 5 carbons, 12 hydrogens everywhere. Are we together? Then we are asked, sometimes, just to say to you, you find that it is given here. Are we together? So you can actually see sometimes is the relative molecular mass controlled or not. Are we clear? Right, so when we deal with isomers, definitely the relative molecular mass is controlled. Then we are asked, are these hydrocarbons saturated or unsaturated? And we can see they are all alkanes, the single bonds between carbon and carbon atoms. So they are saturated. So that will be a mark. We are required to explain the answer. We know it is because the hydrocarbons contain, and I'm writing this because I want to show you what is important. They contain only single bonds. between carbon atoms. So they contain single bonds between carbon carbon atoms altogether. Right. Now, keywords here only. You can't just say they contain single bonds. There's still a single bond between carbon and hydrogen. Again, even alkenes have single bonds between carbon and carbon atoms, but if it is saturated, it must be only single bonds, and those single bonds must be between carbon atoms. Very much keywords, because if you just say it contains single bonds, it's not entirely true. There's still a single bond between carbon and hydrogen. Then one of the hydrocarbons, A, B, or C, has a straight chain with no branches. Write down the following: the letter A, B, or C that represents this hydrocarbon. So we want the hydrocarbon that is not having any branches, and definitely that is A. So our answer there will be A. And the next question said we must write this, its Iupac name. So our answer is A, and the Iupac name, very simple. How many carbons? 1, 2, 3, 4, 5. So the parent chain has 5 carbons. It is a hydrocarbon. It is an alkane, and therefore the name must end with A and E. In other words, the answer there is definitely A. The Iupac name, remember, it has 5 carbons, so it is a pent, and then it's an alkane, so the name ends with A and E. And this is definitely 2 marks most of the time. Then consider hydrocarbon C and its boiling point. Then we are required to write down the structural formula of hydrocarbon C. Right. So we must write down the structural formula of hydrocarbon C. And my dear learners, we have already done that altogether. There's the structural formula of hydrocarbon C. Remember, it's the one with the lowest boiling point. It means it must be the one with the smallest surface area. That is why it has 3 carbons in the parent chain and 2 substituents. So that would have given you 2 marks. Then explain why hydrocarbon C has the lowest boiling point. In your explanation, refer to its structure, intermolecular forces, and the energy involved. And then the 16.6 as well. Which one of hydrocarbons A, B, or C has the highest vapor pressure? Refer to the data in the table to give a reason for the answer. And we know if we want the one with the highest vapor pressure, we know we have to look for the one with the lowest boiling point. So our answer there is definitely C. So our answer there must be C. And we are requested to refer to the data in the table to give a reason for the answer. So we must reason using boiling point. We said C has the highest vapor pressure because, to give an explanation, we say C has the lowest boiling point. C has the lowest boiling point. Then the last question for the day, it's that 16.5.2 that I said we'll just come back to it. So this is definitely 2 marks, 1 mark for the reason and 1 mark for identifying the hydrocarbon with the highest vapor pressure. So we here in 16.5.2, remember we were required to explain why C has the lowest boiling point than all of them. And we must refer to structure, intermolecular forces, as well as the energy. And we note that we said we will always use 3 headings. The first heading is the cause. And the course is the one that is actually going to talk about what? The structure. So you will agree with me that the first mark is that C has the shortest chain length. This is why it has the lowest boiling point. Remember, I am comparing molecules from the same homologous series. So if it's from the same homologous series, you will remember that we have to talk about the chain length. So C has the shortest chain length than A and B. Remember, it is a comparison than A and B. Then we need to talk about the strength of intermolecular forces. So this must be the strength of intermolecular forces. Remember, you are not going to write IMF. So if C has the shortest chain length, we know the shorter the chain length, the weaker the intermolecular forces. So in other words, C has the weakest intermolecular forces. C has the weakest, you will write it in full, it has the weakest intermolecular forces than A and B. And then we need to then talk about the last one, which is energy. So if C has the weakest intermolecular forces, it means less energy is needed to overcome the intermolecular forces of C than A and B altogether. So that will be the first mark, the second mark, and the third mark altogether. So write IMF in full. And that is definitely answering everything. So same tips, my dear learners, analyze your question, note what is important, and get to understand the table that is given as well as the scenario so that you are able to answer all the questions that come up. So do your groundwork altogether because this topic really counts a lot of marks. So that is all I had for you today, my dear learners. Send me questions to stemdigitalschool@africateengeeks.co.za in preparation for our question and answer session. Thank you so much and enjoy the rest of the evening. Goodbye.